Hello, my dear students. Welcome to this class. Today, we are going to discuss about law of mass action. In 1864, Goldberg and Watt proposed this law. According to this law, the rate of a chemical reaction is directly proportional to the product of the active masses, such as concentration and partial pressure of reactants raised to the power of their stoichiometric coefficients. For example, let's take a hypothetical reaction. AA plus BB gives us products. From this law, we can write rate is directly proportional to concentration of A power small a multiplied by concentration of B power small b. So our rate will be, we have to give a proportionality constant K dot concentration of A power small a multiplied by concentration of B power small b. Here the proportionality constant K is called rate constant or velocity constant or specific reaction rate. If we take concentration of A is equal to concentration of B is equal to 1 mole per liter, then our rate will be equal to K dot 1 power A dot 1 power B. That means K. So the rate of a chemical reaction at unit concentration of reactants is called rate constant. The value of rate constant depends on nature of reactant, temperature, and catalyst. Now we are going to learn about a new concept that is called molecularity. What is molecularity of a chemical reaction? The answer is the number of reactant molecules which collide with each other in a chemical reaction to form products is called the molecularity of the reaction. For example, the dissociation of PCl5 gives us PCl3 plus Cl2. Here, one reactant molecules participated in this reaction. So this reaction is unimolecular. The dissociation of hydrogen iodide gives us hydrogen plus iodine. Here, two HI molecules participated in this reaction. So this reaction is bimolecular. Another reaction is 2SO2 plus O2 gives us 2SO3. This reaction is trimolecular. Nitric oxide with ozone gives us nitrogen dioxide and oxygen. This reaction is bimolecular. Carbon monoxide with oxygen gives us carbon dioxide. This reaction is trimolecular. Another reaction is ferric chloride with stannous chloride gives us stannic chloride and ferrous chloride. Here, three reactant molecules participated in this reaction. So this reaction is also trimolecular. Now we are going to learn about properties of molecularity. Molecularity can neither be zero, negative, fractional, and infinite. Molecularity is a theoretical quantity. Molecularity of a reaction cannot be greater than 3 because more than 3 molecules can't collide effectively to form products. Molecularity is independent of pressure and temperature. Molecularity is defined for single-step reaction. But for a complex multi-step reaction, the molecularity of each step is different and there is no meaning of overall molecularity of the reaction. For example, decomposition of hydrogen peroxide takes place in the following two steps. So this is our overall reaction. The first step, hydrogen peroxide gives us water and diamond oxygen. Step 2, two diamond oxygen combine with each other to give oxygen. The first step is generally very slow, and the second step is very fast. For a chemical reaction which is completed in more than one step, the slowest step is the rate determining step. So from the step 1, we can see one reactant molecule participated. So from step 1, the reaction appears to be unimolecular in nature. Now we are going to talk about rate law. For a chemical reaction, AA plus BB gives us products. Rate is proportional to concentration of A power. Let's take a number X multiplied by concentration of B power. Let's take another number which is Y. So we can write rate is equal to rate constant K dot concentration of A power X multiplied by concentration of B power Y. Here X is order of reaction. With respect to A. And Y is order of reaction with respect to B. This is our rate law expression. Let's take some rate law expression and understand the significance of order in a chemical reaction. In the first rate law expression, we can see the order of reaction with respect to A is 1, which means if we double the concentration of A, the rate will be doubled. If we triple the concentration of A, the rate will be tripled. Similarly, the order of reaction with respect to B is 1. That means if we double the concentration of B, rate will be doubled. And the overall order of the reaction will be X plus Y. So here 1 plus 1, that means 2. So the overall order of the reaction is 2. In the second rate law expression, we can see the order of the reaction with respect to A is 2. That means if we double the concentration of A, the rate will be 4 times of previous rate. In the third rate law expression, we can see that the concentration of B power 0. That means the order of the reaction with respect to B is 0. That means if we change the concentration of B, the rate will be same as the previous rate. So the rate will not be changed with respect to B. So in the second rate law expression, the overall order of the reaction is 2 plus 0.5, that means 2.5. In the third rate law expression, the overall order of the reaction is 1 plus 0, that is 1. So this is the significance of order of a chemical reaction. Now we will talk about properties of order. Order of a reaction is an experimentally determined quantity. The second property is order can be zero, negative, and fractional, but cannot be infinity. Order depends on pressure and temperature. For a multi-step complex reaction, the overall order of the reaction is determined by RDS. That means our rate determining step. For example, 2H2 plus 2NO gives us nitrogen plus 2H2. This reaction is completed in 3 steps. Step 1, two NO gives us N2O2, and there is a equilibrium between them. So for a equilibrium, we write an equilibrium constant K1, and this step is very fast. Step 2, N2O2 with hydrogen gives us N2O and water. And this reaction, we write a rate constant K2, and this step is very slow. In step 3, N2O plus hydrogen gives us nitrogen with water. And this step is very fast, and we write a rate constant for this reaction, and that is K3. We have to determine the order of the reaction. As we previously discussed that whenever a reaction is completed in more than one step, the slowest step is our rate determining step, or RDS. Here, step 2 is the slowest step. So step 2 is our rate determining step. So from step 2, we can write rate is equal to rate constant K2 dot concentration of N2O2 multiplied by concentration of H2. Now, this N2O2 is not in our overall reaction. This is an intermediate. So we have to eliminate this intermediate from our rate expression. So in step 1, we can write equilibrium constant K1 is equal to concentration of N2O2 divided by concentration of NO, and the coefficient 2 will go to power. So we can write concentration of N2O2 is equal to K1 multiplied by concentration of NO power 2. Now we replace this in this equation. We will find rate is equal to K1 K2 concentration of NO power 2 multiplied by concentration of H2. This K1 K2 gives us another constant. Let's say K prime. Concentration of NO power 2 and concentration of hydrogen power 1. So the order of the reaction is equal to 2 plus 1, that is 3. So now we will be able to find out the order of a complex reaction. Now we will discuss about the unit of rate constant. This is very, very important. For a reaction, we can write rate is equal to rate constant multiplied by concentration power small n. Here, n is our order of reaction. So we can write rate constant K is equal to rate divided by concentration power n. Unit of rate is mole per liter per time, and the unit of concentration is mole per liter power n. So we can write mole per liter to the power 1 minus n per time. If n equal to 0, that means the reaction is a zero order reaction. So the unit of rate constant will be mole per liter per time. If n equal to 1, that is a first order reaction. So the unit of rate constant K will be time inverse 1. If n equal to 2, then the reaction will be a second order reaction. So the unit of rate constant will be liter per mole per time. So just by seeing this unit, we have to find out the order of a specific ratio. So this unit of rate constant will be very helpful when we will practice mathematical problems regarding different reactions of different order. So this is our discussion about law of mass action, rate law, molecularity, and order of reaction. So I hope you understood the concept very well. Thanks for watching the video, and don't forget to like, comment, and subscribe.